So today we're doing adding vectors using basic right triangle trig. In other words, all the vectors that we set up today are going to be at right angles to each other. Before we jump into that though, I want to give a reminder, a refresh about the math. So we have four things that we're going to be using: Pythagorean theorem, sine, cosine, and tangent. Now Pythagorean theorem, remember, is a squared plus b squared, that's the two sides of the triangle, equals c squared. That's the hypotenuse of the triangle. Sine is sine of an angle, sine of theta equals your opposite over your hypotenuse. Cosine of an angle equals the adjacent over our hypotenuse. And tangent of an angle is going to equal opposite over adjacent, the opposite side over the adjacent side, not involving the hypotenuse at all. So if I have a right triangle here, let's get ourselves a decent right triangle, and here's angle theta right here. This would be the hypotenuse side, this would be the opposite side, and this would be the adjacent side right here. So for Pythagorean theorem, right, A and B would be either side, doesn't matter which one you chose, either side as long as it's not the hypotenuse, and the hypotenuse is always C over there. For sine theta, your opposite is opposite based upon whatever angle you choose. So we would be choosing opposite over hypotenuse based upon the angle given or the angle chosen, and I chose this to be my angle, so here's my opposite, and my adjacent is the side that's actually touching the angle. Hypotenuse never changes no matter what angle you have. Another reminder for you: if you need to get at the sine, please make sure your calculator's in degrees, but if you need to get at the theta or at the angle that's trapped inside the sine, the way you do that is by arc sine or inverse sine. So if you take the inverse sine of both sides here, theta equals sine inverse of opposite over hypotenuse, right? And likewise for the others. Now I'm going to use these concepts to solve some basic vector problems here in the upcoming slides. I'll let you know whenever I'm about done with one slide and I'm going to move on to another, in case someone needs the video to be paused so they can finish copying down what they see before we jump into the next one. All right, so a plane takes off from from Philadelphia, flying to Los Angeles. Let me get a terrible plane here. Capable of flying 250 meters per second. So here we go, right, and encounters a 25 meter per second wind hitting directly on its side. Now I'm going to purposefully position that 25 meter per second vector at the tail to tip position over here. Remember, it doesn't matter where I put a vector as long as the magnitude, that's the length or the number here, 25 meters per second, and the direction, it's hitting directly from the plane side, so it's coming like this straight down on it. Okay, you could have it going up and it wouldn't matter here, it would just change how the problem is being referenced. Instead of drawing it here coming down, which that would be fine, I'm just going to draw it over here, that way it's tail to tip, which means the resultant of these two vectors is completing the triangle, right? Which is going to be the resultant velocity. So I have the one side here, 255 meters per second, going from Philadelphia to LA. So actually, let's get this in, PHL and then LA, right? And then the resultant vector, R, is going to be the addition of my 255 meters per second, the plane trying to go that way, and the 25 meters per second, the wind pushing it off course. So to solve for my resultant vector r, notice I have a right triangle here. I'm just going to use right triangle trig, specifically Pythagorean theorem. A squared plus b squared equals c squared, where c here is r. So I have 255 squared plus 25 squared equals r squared. So now I'm just going to work a little bit of math and come out with my answer. So I put all the stuff on the left-hand side into the calculator, come out with 65,650. Now I need to square root both sides, right? And R comes out to be 256 meters per second. Now I do have a problem here. This should make sense to you. A 25-mile-per-hour wind isn't going to increase the speed all that much. But check out my sig figs here, right? This actually kind of messes things up. Because of sig figs, the way I would have to report this is just 260 meters per second. Really, the most difficult part about all these problems is figuring out where to draw your vectors and drawing the triangle. Just reading along, the plane capable of flying at 255 meters per second going from Philadelphia to LA, so this line, 255 meters per second, should make sense. I just draw a line. It's this 25 meters per second. The wind hitting it directly on its side, so you might say, hey, I should draw it right here. Well, yeah, that's fine. That's good, in fact. But what I'm trying to point out to you is vectors can be slid. They can be moved. But I'm moving the entire picture. But if I take instead the vector here and I slide it over tail to tip, right, then I get a nice vector, a resultant vector, which should make sense to you logically that this is the resultant. Because if we're flying to LA and the wind is coming this way, it's going to push us off course a little bit like that. Thus, my resultant vector. All right, two other types of problems that you might see with this. The first one was proportions, and the second one we're going to get to. We'll see if I have room to do it here. But the first one just uses direct proportions with triangles. So a pilot takes off from Philadelphia to Los Angeles. It's the exact same triangle, right? So I've got here, right, and the wind's taking us off course, right? And notice I changed the wind this time to 5 meters per second. And we said, I forgot to write this down again, but we said the plane was capable of flying 255 meters per second, okay? And then you have your resultant, right? Here are, but this isn't looking for the resultant of this triangle. Instead, it gives some other details here. So let's change colors. It says that the distance between them is 3,870 kilometers. Well, remember, kilometers means times 10 to the third here. Okay, so 3,780 times 10 to the third meters, and then asks how far off course will she be when she tries to land. In other words, what is delta x here? So she's able to fly, or the pilot's able to fly 255 meters per second that far along that lane, okay, if going straight from Philadelphia to LA, right? But there's a wind that sweeps directly down, right? How far off course, how far directly off course are we going to be? Delta x. Now this is proportions, okay, this is proportions. This we're going to set up 255 is to 3,870 times 10 to the third, and that's in meters, right, is the same as, now I put velocity up on the top, so I need to put velocity on the top again, 5 meters per second to delta x. And now I solve the algebra. The way I do that, remember, cross multiply. So I'm going to crisscross here, come out with 255 delta x equals, and now I'm going to run out of space, but 5 times 3,870 10 to the third. So now whenever I actually work the algebra here, I come out with, dividing both sides by 255, you come out with delta x is going to be 75,882 meters, or using significant figures, right? Only one sig fig here. It would be 80 kilometers. And so just an interesting side point here. A little small wind, 5 meters per second, blowing on a plane that's flying a really, really long distance. all the way across the country, can take a plane off course, way off course, right? 80,000 meters, 80 kilometers off course. The pilot really, really has to account for that slight shift that needs to be made to offset that 5 meter per second wind. So let's do that problem next. So the plane now is going to turn up into the wind, flying at a cruising speed of, and let's scratch this here. Let's go back to what we actually are using, 255 meters per second, right? And the wind's going to pull it back down at 5 meters per second here. So we had to turn slightly into the wind now to be able to go along a side directly from Philadelphia to LA. Notice now in the triangle, whenever I turned into the wind, the speed of the plane, 255 meters per second, became the hypotenuse of the triangle, and our resultant vector, or what we'd be looking for if we were calculating speed here, is now the base. All right, so please make sure of that, and ask what would be, what angle should the plane take? So I'm looking for here theta, right? And then what would be the resultant speed? And so I labeled that r. Now, by the way, I would expect r to be slightly less because it's actually not the hypotenuse anymore, it's the base side. So now to find the angle, I'm going to use sine, because here's my theta right here, right? There's theta, and this is the opposite, and this is the hypotenuse. So sine theta equals opposite, which is 5, over the hypotenuse, 255. To get theta by itself, I take the sine inverse of both sides, so I get theta equals sine inverse of 5 divided by 255, which comes out to be 1.12 degrees. And if we're keeping with 1 sig fig here, right, because of our 5 meters per second, I just have to make this 1 degree. So notice just a 1 degree difference in the angle makes a massive difference whenever we're talking about how far this plane actually goes up here. All right, so big difference, right, with how far off course that 1 degree can end up making. Now another thing here, we need to find the resultant, right? So now let's go ahead and let's solve for r. To do that, I can just once again use Pythagorean Theorem. A squared plus b squared equals c squared. So let me skip over my stray mark that randomly got there. I'm going to call r to be a here. Remember, it cannot be the hypotenuse because that's c. It's not the hypotenuse, so it can't be that. It has to be a or b. So I'm going to call it a. So r squared plus 5 squared is going to equal 255 squared. So something along those lines. And now it's just algebra. So r squared is going to equal whatever 255 squared minus 5 squared is. So whenever you work this math, 255 squared minus 5 squared comes out to be 65,000, and then you take the square root of that and you get 254.9 meters per second. So that's not a big difference whenever you really, it's hardly any difference at all. 254.9 meters per second. So let's get my 0.9 in there. But this isn't going to matter, right? Because of sig figs, unfortunately, I only gave us 1, so this would have to become 250 meters per second. Thankfully on the test I'll make sure to catch that and give us more sig figs. So a slight difference in the wind doesn't take away much velocity. It doesn't require you to turn into it by much, just 1 degree is how far you got to turn into the wind. But if you neglect it, you're going to be 80 kilometers off course. You're going to miss Los Angeles.